the first thing I want to talk about is Maxwell's views on statistical mechanics and thermodynamics, because I think they're very interesting and at least should be a position that's on the table for serious consideration. I actually think he's right. And then I'm going to talk about a way of thinking about probabilities in statistical mechanics that I think fits naturally in with the Maxwellian view. So there he is. Maxwell is a young man. He never got to be an old man. He died at the age of 48. And if you think about everything he accomplished in that time period, it's very humbling. By the time Maxwell was my age, he'd been dead for 2 years. I'm going to start out. Prefaces. I probably should have thrown this into the introductory lecture, but I ran out of time. This is an instructive example that shows up in the textbooks a lot. And it has to be, suppose you've got a box that has gases of the same temperature, partition in the middle has gases of the same temperature and pressure on both sides, and you pull the partition out and let them interfuse and mix and interfuse. Has entropy gone up or not? It's a question for the students. Yeah.
Yes, if they're different in size or there's some sort of different property.
Yeah, that's the standard textbook answer. That's the answer that Maxwell, and when people started discussing this, Maxwell and Gibbs and all those people, that's the answer that they gave. If they're different, if it's the same kind of gas, no. You've just started out with a certain sample of gases, a certain temperature and pressure, and you ended up with that. But if they're different, then yes. There is an entropy increase, and it's basically the entropy increase would correspond to this gas expanding into this volume plus the entropy increase associated with that gas expanding to that volume. And there's a sort of textbook device that people use to show that that's the right answer. This is an irreversible process, but if I actually want to know the entropy difference between two equilibrium states, no matter how it got from one to another, if you can imagine a quasi-static reversible process that joins them, then you can calculate the entropy difference between those two states, because the entropy difference between those two states is
Can you tilt that forward?
Yeah. Is that visible to everyone now?
Uh-huh. Yeah.
Okay, good. Where you take the integral across some QSR, along some QSR process. And the standard textbook device, which actually is due to Boltzmann, is imagine you've got some kind of membrane that's permeable to one gas and not the other. So suppose I've got some kind of substance that I can make a piston out of, such that the blue molecules just go right through it, but the yellow star molecules bounce off of it, and then I can hook it up to a heat bath and slowly and isothermally expand the thing while doing work raising away. And during that time, a certain amount of heat is going to go, is constant temperature, and a certain amount of heat is going to go into the gas, and so the entropy increase is just going to be that amount of heat divided by the temperature. And then I can do it with that one. When I get that on there, get back to it. Okay, is that an irreversible process? I mean, the original one, the free expansion. Yes. Yeah, we usually say that, but is it impossible that that these guys will ever be back into the original compartments again?
Yes, we have to do work. If you have semi-permeable,
Or you have to be very clever.
Or very clever. Or very lucky.
Yeah, the potatoes rules.
Right. Yeah. Well, it depends on how many it depends on how many molecules I have there. But yeah. Yeah, I mean, if these things are bouncing around effectively at random, they could just sort of happen to end up back in the original chambers. If it's a large number of molecules, the probability of that happening at any given time is going to be astronomically small, and the amount of time you'd have to wait before you could expect that to happen would be an incredible amount of time. That, as David said, the walls of the container would decay or something like that. But I mean, if you really take seriously the idea these things were bouncing around effectively at random, it could happen in the next 5 minutes. It's just bloody unlikely. Now, why am I emphasizing that? Because the original statements of the second law of thermodynamics, the Clausius and Kelvin thing, declared certain processes to be impossible. What Nick said, it's impossible to separate those without expenditure of work. That's what the original version of the second law of thermodynamics is. And if you take the kinetic theory seriously, it's not impossible. It could happen. It's just bloody unlikely. And that's worth emphasizing because Maxwell and others fairly early on realized that if they were going to get anything like the second law of thermodynamics out of kinetic theory, it would have to be a modified version and not the original version. According to the kinetic theory of gases, the second law of thermodynamics, as originally conceived, is false. And I think that's not widely recognized among physicists these days, because they don't really distinguish between the original version of the second law of thermodynamics and the modified version that we accept today. And that's, if you've looked at the literature on theory reduction, that's something that's sort of a commonplace in the literature, that sometimes you have to, you start with a, I always forget which is reduced and which is reducing. But you start with one theory, and you want, if you've got a more fundamental theory, sometimes you have to correct the original theory. You don't have to get the original theory back with a slightly modified version of it. And this, I think, is a case of that. Here's Maxwell writing a letter to an editor of the Saturday Review in 1868, trying to explain the sense in which he thought, according to kinetic theory, irreversible operations are irreversible. This is a simple instance of an irreversible operation, which I think depends on the same principle. Suppose so many black balls put at the bottom of a box and so many white above them. Then let them be jumbled together. There's no physical difference between the white and black balls, I guess other than the color you mean. It's exceedingly improbable that any amount of shaking will bring all the black balls to the bottom and all the white to the top again. So the operation of mixing is irreversible unless either the black balls are heavier than the white, or a person who knows white from black takes them up and sorts them. Irreversibly, and he means, effectively irreversibly, because he doesn't say impossible, he says exceedingly improbable. Thus, if you put a drop of water into a vessel of water, no chemist can take out that identical drop again, though he can take out a drop of any other liquid. So, put water into water and say, I want you to pull out exactly that same drop of water we put in. Can't do it. where if there's a drop of alcohol, then some chemical means might be able to separate them, or other, more physical means.
What did he say about he said that same principle, which is?
The same principle, okay, the paragraph before is about mixing of gases. So, same principle that governs the irreversible mixing of gases. And we have something similar in Gibbs in 1875. He's talking about the mixing of gases, and he says, well, okay, yeah, like there's a section, as Yost pointed out the other day. This paper from 1875 is primarily about thermodynamics, but there's this one section called, I think, on the molecular constitution of matter, or something like that. And he talks about what mixing of gases looks like from the point of view of a molecular theory, and what he says is that spontaneous separation of those gases is impossible, and that would count as a uncompensated decrease of entropy, but it's not possible, it's improbable. So again, Maxwell says it. Put that quote. Actually, I'll come back to it. So yeah, Maxwell and Gibbs are acknowledging that the second law of thermodynamics, as originally conceived, can't be quite true on the kinetic theory, but some kind of modified version could be true. Something of the flavor that says what the original version deems impossible is merely very improbable, and in the cases of systems of macroscopic many molecules, perhaps so improbable to be as effectively impossible. And so, I mean, I think that something like this, something of the flavor of this, is what most physicists these days have been thinking. Is that even though there are going to be local fluctuations of temperature and pressure in a gas or other liquids or things, there isn't, you can't rig up any kind of process that would consistently and reliably exploit them to transfer heat from a cooler or warm body without producing a compensating increase in energy elsewhere. Something like that, I think, is believed by most physicists. Maxwell again. This is from a review of Tate's thermodynamics, in which he praises Tate for his handling of the second law. We have correspondence between Maxwell and Tate, where Maxwell is giving Tate advice on what to say about the second law. In a sense, he's praising Tate for taking his advice. If we consider a finite number of molecules, the average properties of this group, though subject to smaller variations than those of a single molecule, are still every now and then deviating very considerably from the theoretical mean of the whole system, because the molecules which form the group do not submit their procedure as individuals to the laws which prescribe the behavior of the average or mean molecule. Basically, there might be laws considering about averages, and those are going to be the laws of thermodynamics, but individuals don't all conform their behavior to the mean behavior in their fluctuations. Hence, the second law of thermodynamics is continually being violated. In fact, to a considerable extent in any sufficiently small group of molecules belonging to a real body. So not only, so he's not just saying that, violation is improbable. He's saying it's happening all the time, but it's happening, say, at a microscopic level. It becomes negligible when you're dealing with very large numbers of molecules. Says the calculation belongs, of course, to molecular theory and not to pure thermodynamics, which shows that we have reason for believing the truth of the second law to be the nature of a strong probability. And by the way, Poincaré took this to be an objection to the kinetic theory. one person's modus ponens is another person's modus tollens, because Poincaré's attitude was, okay, you've got this theory which entails the falsity of a well-established law, second law of thermodynamics. I'm not going to reject the second law of thermodynamics on the basis of speculations about molecules. And though he also said, if it turned out that, how do you pronounce that guy's name? G-U-O-Y. G-U-O-Y, French physicist who was doing stuff on Brownian motion. Anyways, the French physicist who's doing stuff on Brownian motion, Poincaré did say that if he's right that Brownian motion is agitation due to molecules, then yeah, second law of thermodynamics is false, because a Brownian particle in a gravitational field sometimes goes up a bit, and it's heat that's doing that. So you have heat being converted entirely into work without a compensation. Okay. All right. Let me talk a little bit about Maxwell's demon. Maxwell's demon first appears in a letter from Maxwell to Peter Guthrie Tate. I think he's commenting on a draft of Tate's book on thermodynamics, and he's suggesting, well, in this book you might want to pick a hole in the second law of thermodynamics. Everyone's familiar with the setup of Maxwell's demon? What does Maxwell's demon do? Somebody? Yeah, Jesse?
Decreases entropy by operating some kind of, by making fast particles all collect in one side of the box and slow particles all collect on the other side of the box.
Yeah, that's the setup. You've got a box of gas, and Maxwell, as Jules mentioned, one of the things he was interested in, one of the things that differed, one of the differences between Maxwell's work on kinetic theory and the people who went before him, is Maxwell didn't treat a gas as if it's a bunch of molecules all traveling at the same speed. He actually inquired into the velocity distribution that you ought to expect, and concluded it would be what we now call the Maxwell-Boltzmann distribution. That means that if I've got a gas at a certain temperature, there's a variation in velocities among the molecules in the gas. Some are going faster and some are going slower. So Maxwell's thinking about this. It says, okay, suppose I've got a gas. I've got a partition down the middle. That partition has a little trap door in it. And there's this little guy. Maxwell claims that it was Kelvin who gave it the name of demon. Kelvin claims it was Maxwell. So anyways, at a certain point, someone started calling it a demon. And what he's going to do is, he's got a trapdoor, well-oiled hinges, so he can open and close it without doing any work. And what he's going to do is, if a fast molecule is coming from the left to the right, he's going to let it through, but otherwise not. If a slow-moving molecule is traveling from the right to the left, he's going to let it through, otherwise not. And he's going to collect fast molecules on one side of the box and slow molecules on the other side of the box. And he's going to create a temperature difference without doing any work. Probably can create a pressure difference too. And Maxwell also says you can do pressure differences. And Maxwell first introduces the demon to the world. First public writing is in his theory of heat. There's this chapter, there's a section towards the end called Limitation of the Second Law of Thermodynamics. So now there's an undated letter from Maxwell to Tate, sometimes called the Catechism Concerning Demons. And it says, what are they? They're very clever beings that can manipulate individual molecules. Who first gave them this name? Thomson. What's their purpose? To show that the second law of thermodynamics has only a statistical certainty. Now, it's easy to read that as Maxwell is saying that the second law of thermodynamics, as strictly as originally conceived, isn't true, but that he's advocating something like the probabilistic version that I had up. I think that's not quite right. First of all, if it was supposed to show that the original version of the second law isn't right, it's actually not needed. In that quote earlier from his review of state thermodynamics, he says, even in the absence of demons, the second law of thermodynamics, as originally conceived, is continually being violated on a small scale. And what the demon does is exploit small scale fluctuations, small violations of the second law, to build up the big one. So the demon doesn't get started unless those fluctuations are there, so the demon can't get started unless the original second law is false. And the probabilistic version I had up a moment ago said that there wasn't any process that can consistently reliably harness those fluctuations. So big decreases of entropy are improbable. But if there were such a demon, a large decrease of entropy would not be improper. Or I don't want to beg the question whether it counts in that context as a decrease of entropy load. I shouldn't say that. A large build-up of a large temperature difference without doing work isn't improbable, but probable. If to the second law of thermodynamics as originally conceived has to be replaced by the probabilistic version, which is the sort that most people accept, it's a spectacularly ill-chosen example. So let's go back to what he actually does say. So this is the passage that I mentioned earlier from his book, The Theory of Heat, called Limitation of the Second Law of Thermodynamics. He says, one of the best established facts in thermodynamics is it impossible in a system enclosed in an envelope which permits neither change and fall, in which both the temperature and pressure are ever the same, to produce any inequality of temperature or pressure without the expenditure of work. This is undoubtedly true as long as we can deal with bodies only in mass and have no power of perceiving the separate molecules of what they're made up. That's the limitation he's considering. It's true as long as we can deal with bodies only in mass and have no power of perceiving the separate molecules of which they're made up. So the truth of even a probabilistic version of the second law of thermodynamics for Maxwell is restricted to situations in where we're dealing with macroscopic bodies on a macroscopic level. If we conceive of a being whose faculties are so sharpened that he can follow every molecule in this course, such a being whose attributes, or that's the title, are still as essentially as finite as our own, would be able to do what is present and possible to us. Then he describes the setup that I just described, and he says, he will thus, without expenditure of work, raise the temperature of B and lower that of A in contradiction of the second law of thermodynamics. At present, impossible to us. He's deliberately leaving open the prospect that with development of technology, we might be able to get to the point where we can manipulate molecules on an individual basis and be able to make little gadgets that can do this, which would be really cool. Because then we wouldn't have to be using the steam engines to rip open the hills and go for coal. We could power the steam engines with these little demonic devices without burning any coal. So the limitation, the version of the second law of thermodynamics that Maxwell has in mind has a further limitation. It's actually weaker than the one that most people accept these days. It's a limitation to situations in which we don't have the ability, there's no manipulation of individual molecules. Okay. Then concludes, this is only one of the instances in which conclusions which we have drawn from our experience of bodies consisting of an immense number of molecules may be found not to be applicable to the more delicate observations and experiments which we may suppose made by one who could perceive and handle the individual molecules which we deal with only in large masses. All right. So, there's the original version of the second law of thermodynamics, which will be the first. We call the first second law of thermodynamics. There's the probabilistic version that I think is accepted by most physicists today. We might call the second law of thermodynamics. But Maxwell is actually proposing a distinct alternative to both of them. All right. Okay. And part of the reason I'm interested in this is that all this fits well with Maxwell's views on the nature of thermodynamics as a science. What kind of science is thermodynamics? What do the concepts work, heat, and entropy actually mean? And one thing that I emphasized in the introductory level is that to formulate the second law, you need to be able to distinguish between two ways that energy can be transferred from one body to another. You can do work, or it can be done as heat transfer. And we're not supposed to think of heat transfer as a substance, but a particular mode of exchanging energy between two. Now, one thing that what is the difference between those two? This is from a nice popular book by Peter Atkins called 4 Laws That Drive the Universe. The 4 laws are meant to be the 4 laws of thermodynamics. The 3 laws plus the 0th law. And I like this illustration. What does the distinction between doing work and heating something look like on the molecular level? Well, on the if I'm doing work on my surroundings, I may be driving a piston out and I'm pushing things up in a sort of orderly way. Whereas if I'm heating my surroundings, then I'm just sitting there and jiggling my molecules, and the molecules, the energy gets transferred to the environment in a kind of table-gated way. So doing work, he says, results in the uniform motion of atoms in the surroundings. Heating stimulates their disorderly motion. And Maxwell says something similar, but with slightly different emphasis. On the distinction between available energy, say potential energy that we might have stored in a system by, say, doing work on it and raising a weight. Available energy, whereas then there's dissipated energy, which is dissipated as heat, which isn't so useful. Available energy is energy which we can direct into any desired channel. Dissipated energy is energy we cannot lay hold of and direct at pleasure, such as the energy of the confused agitation of molecules, which we call heat. Now, confusion, like the correlative term order, is not a property of material things in themselves, but only in relation to the mind which perceives them. And there's this interesting metaphor. He says, a memorandum book does not provide as neatly written appear confused to an illiterate person or to the owner who understands it thoroughly, but to any other person able to read it, it appears to be inextricably confused. And I think what he's imagining is that if you're the sort of person who keeps a memorandum book, you develop a certain shorthand you use that only needs to be Actually, we saw a moment ago that Maxwell and the physicists he corresponds to had certain abbreviations and jargon that they would use among themselves that wouldn't necessarily be comprehensible to others, like using theta, delta, delta, ICS for thermodynamics. So if you're writing neatly, an illiterate person would say, okay, that's nice, neat handwriting. It looks, it doesn't look confused. To the person who reads it, who owns the memorandum book, it doesn't seem confused, doesn't read it. But the person, anyone other person able to read, it appears to be infinitely confused. It says, similarly, the notion of dissipated energy could not occur to a being who could not this notion of dissipated energy could not occur to a being who could not turn any of the energies of nature to his own account. That would be like the illiterate person. If you had no ability to manipulate anything, you would never formulate a distinction between those two modes of energy transferring. You would never distinguish between heat and work. You would never worry about the dissipation of energy because you can't do anything, right? So if I can't do anything, then energy doesn't pass from a form that's useful to me to a form that's not useful to me. On the other hand, if I were a Maxwell demon, if I could keep track of all those molecules, then it wouldn't matter. Again, the distinction wouldn't occur to me because energy would never pass from a form that is useful to me to a form that's not useful to me because it's always useful to me. So if energy is never useful to you, you don't need the distinction. The distinction of heat and work wouldn't occur to you. If it's always useful to you, the distinction between heat and work wouldn't occur to you. But it's only to beings like us, beings in the intermediate state, who can lay hold of some forms of energy while others of Lewis graph, that energy appears to be passing inevitably from the available to state. Now, I just want to add a comment that I don't think is in Maxwell. It's probably true that any kind of being that we could think of as having agency would have to be in that intermediate state. That we have to be composed of many molecules, and we have to be big on the scale of molecules. And also, this is something that what David Wallace was, I thought, and he was thinking about what David Wallace is doing, something like that. The variables that such a being could exploit would really have to be the ones that have a relatively autonomous dynamics. And so, even if there's a agent-relative aspect to this, there might be good principal reasons to think that it doesn't matter too much the details of what sort of agent there are, because we're all going to be able to manipulate more or less the same kinds of variables.
Wait, I don't understand. What? And you yourself were allowing, a few minutes ago, for technological advancements, whereby we could, it seems like there's not a clear upper limit on the extent to which we could extend our control.
Well, Maxwell was. Right. I was actually pointing out that
but
Maxwell,
what are the
Maxwell
reasons
does.
to think otherwise?
Right, that's a good question.
What's the answer?
I don't know. I mean, what I guess suggested was more or less on the matter of a conjecture. I actually think that this is a very deep question that I don't think that anyone has a good answer to. Do we have good reasons to believe that you couldn't make a nano machine? They could be a Maxwell demon. There's this lovely pair of papers by Ehrman and Norton where they go. Since Maxwell's time, there's been a vast literature on how to exercise the demon. Arguments that such a demon is impossible, which of course was not Maxwell's idea. Maxwell actually, I think, imagined that we perhaps one day we'd ever do it. So, and I mean, one of the other thing, what Ehrman and Norton do is they go through these arguments and divide them into sound and profound. A sound argument would be, one that correctly gets a conclusion but presumes the truth of a probabilistic version of the second law of thermodynamics. You can give arguments of that form, and they're sound, but they don't. But the sense in which they beg the question. A profound one would start from some independently motivated principle. I don't think there's been any successful attempt to do that. So basically, I mean, if we have reason to think it's impossible, it's that every time that everyone's tried to do it, you have a proposal to try to do it that looks initially like it's going to work, and then you analyze it closer and you realize you've forgotten certain kinds of fluctuations at molecular level. So yeah.
But look, there are two. The history of sort of discussions about whether there could be a Maxwellian View. It seems to me there are two components of this.
Okay.
There are two questions, or you can divide it into two questions. Question one is, can we ever imagine the development of technologies? Can we ever imagine the construction of some kind of a machine which could manipulate things at this microscopic level? Second question, if there could be such a machine, what would the evolution of the entropy of such a machine look like in the course of doing these manipulations? Now, all of I've never heard an argument, I mean, somebody can correct me on this maybe, I've never heard of some kind of principled argument that the first thing is impossible, that building such a machine is impossible. The arguments against Maxwell's demon always take the form of trying to argue that if you had such a machine, its own entropy would rise in the course of its operations more than it lowers the entropy of the target system. Those arguments
the first one, actually it's completely settled. There's this wonderful movie on the internet, which is a cartoon in which the individual entities are atoms. And they can position the atoms so perfectly that you can actually have this, it took a huge amount of effort to do it. It's really quite striking, but they were creating huge quantities of entropy.
So what I meant was, when I say could there be such a machine, could there be a machine that would manipulate molecules to produce a decrease in entropy without a compensating increase in entropy? So that was actually part of Maxwell's description of the demon, that he produces a temperature difference without a compensating increase in entropy.
Now that's a much more Freud history, and I think
that's what I meant.
I think a lot of the historical arguments against that don't go through well. But so it seems like everybody's agreed that if we forget about the cost and entropy to the demon, there's no obvious reason why we can't manipulate things at as fine a level as we like.
That's absolutely right. Yeah, that's absolutely right. Yeah. So yeah, what I meant was a demon that manipulates these molecules and produces, say, temperature inequalities without a compensating increase in entropy.
But I think to understand this quote, you would have to proceed from the other direction. I mean, it's not like anybody is necessarily doubting that there are limits to how far we can develop technology and whether we could not continue and in this manner build ever more delicate machines. It's simply a historical fact that people have come up with something like the second law of thermodynamics. And what Maxwell is saying is this notion could not have come up to anybody except from some persons whose epistemological and manipulative powers are somewhere in the middle.
But I mean, if we had the sort of machine that was doing what David said, is manipulating individual molecules, but having a corresponding increase of entropy, then we still have to, at the level of that machine, be able to talk about increase of entropy, which means that we have to talk about the distinction between the machine doing work and heat flowing in and out of the machine. And so there still has to be a distinction between useful energy and dissipated energy to even talk about that. But he's saying is, imagine, to a demon, there wouldn't be, like, because imagine I'm a demon and I regard the whole world as my playground. There isn't any energy I can't direct it to any channel I want. And David comes along and says, okay, you're producing this, this temperature inequality, but you're doing the expense of, an increase of entropy of your surroundings or of your working substance stuff. And you say to this demon, well, what do you mean by increase of entropy? And you say, well, okay, this is what I mean. Well, what is this dq? Oh, that's energy transfer as heat.
Right, but so on this way, I mean, this relates to the conversation we were having at the end of yesterday, and I talked with David a little bit about this afterwards. So I walked out of that conversation, and I saw what you guys were saying, but the notion of entropy that you guys were defending in that conversation essentially amounts to the definitional impossibility of building a Maxwell's demon. That is, whatever you manage to build, you change your definition of entropy accordingly so that it's not reducing the entropy of an isolated system.
Yeah, right. And that's why I paused earlier when I said entropy increase, and I actually should have said it on an earlier slide. Is there something that could reliably produce a temperature difference without a compensating entropy increase? Because on the view that Maxwell is developing, the distinction of heat and work is means relative.
Right.
And if I gain new means to do stuff, then energy transfers that I previously thought as heat, I might count as not dissipative. And so I'll change my estimation of what entropy differences there are. So then it becomes, it maybe becomes a tautology that
well, but that's interesting. Although on your reading, it's often said, I often say, talking about this, it's kind of misleading and unfortunate that Maxwell called this a demon. It gives you the impression that it's something supernatural or something like that. But actually, on the way you propose to read it, that was a wise choice on his part. That is, if this was something that one could actually mechanically realize, then it would have already shifted the definition of entropy in such a way that it wasn't reducing the entropy.
Right. And I mean, one way so the idea that the idea is that there's this means relative distinction between heat and work, and hence a means relative way of estimating what entropy changes between two states. And actually, so let me guess two more quotes from Maxwell, and then I'll illustrate that. He says, we have only to imagine, suppose our sense of sharpness is such a degree that we could trace the motions of molecules as we easily can, and the distinction between work and heat would vanish. Well, if the distinction between work and heat vanishes, then you can't even write this down, right?
Good.
You can't even formulate the second law of thermodynamics if you don't have that distinction. So back to the second, maybe one way to illustrate that is, imagine two agents, one of whom doesn't know of any differences between those two kinds of molecules. Say Bob doesn't know, thinks that those two molecules are the same on both sides, and Alice has, she knows there's a difference, and she has, in her back pocket these semi-permeable membranes. Well, Bob is going to count the initial and final states of that gas as the same thermodynamic state. And then what Alice would when Alice does that thing about raising those weights using those semi-permeable membranes, it looks to Bob like Alice took heat from the heat bath and used it in its entirety to raise those weights without a compensating increase of entropy anywhere. And he's going, okay, you have violated the second law of thermodynamics. Whereas Alice is saying, no, I didn't. You're just calculating the entropy difference between those the initial and final states wrong. If you do it properly and taking into account the fact that those gases are different, there actually was an entropy increase of the gas. Yeah.
I'm sorry, I keep interrupting you. And I don't think there's anything really deep at stake in what I'm about to say. Maybe it's just nomenclature.
Right.
But because everything on the level of statistical mechanics is clear.
Right.
But if you think of entropy the way you're proposing and the way Maxwell seems to be proposing, then it becomes the case that the second law just doesn't have any, lawful, technologically independent content as a claim about the way the world is, or the way the world could legally be.
It ends up being something close to a tautology, or maybe a tautology.
Right.
Yeah.
Okay, good.
Yeah.
Good.
Yeah.
Good.
Yep. I have to think about which of those things.
As long as you keep the level of your technical manipulabilities fixed,
Right.
it does make statements which are true or false in the world.
Sure.
Right.
Sure.
It does have empirical content.
Right.
Yes, I agree.
Yeah. So if I fix, here's the point. If the entropy difference between two states is relative to a means relative distinction in heat and work, then given any such distinction, keep that fixed. There's a determinate entropy difference between any two states, and Alice with her semi-permeable membranes will be able to produce an uncompensated decrease in entropy as measured by Bob's. And one thing I just want to point out that you might think, okay, all of this goes away at the statistical mechanical level, but entropy is just entropy is just minus k integral rho log rho, and that identification that gets to that. You start with canonical ensemble. Canonical distribution, and then the version that Jos did, imagine that one of the volume is one of the parameters in the Hamiltonian. But the thing that's in Gibbs is actually more general. It says, imagine there's a number of parameters in Hamiltonian which are by means of which changes of which I can do work, and then you partition the change in total energy to so there's these call those parameters AI, and then there's these generalized force terms di H by di I. So sum over all these. That's the work term, and then everything else is heat. And then you do the calculation, and you say, okay, I want that heat term to be equal to TdS, and that's what gives you that S. So that depends on identification of certain parameters in Hamiltonians as the ones that you can manipulate to do work. And if someone comes along and say, well, I can manipulate something else, then they're going to get a different entropy. All right, so the view of workers is, as I was saying, the distinction between heat and work as means relative has to do with which variables can be manipulated. Thermodynamic entropy is also means relative. And I think that Maxwell's view is if we were Maxwell's demons, we never would have formulated thermodynamics in the first place. And so it's, you know, I think it's interesting that Maxwell's superhuman being I ended up calling a demon, and Laplace in the philosophical essays on probability also imagines a superhuman being that he doesn't give a name, but we call Laplace's demon. Laplace, he's explaining in the beginning of the philosophical essay of probabilities why there should be a science of probability at all. Because he takes for granted that his readers think that the laws of physics, the laws of nature are deterministic. So everything's determined. Why they have the probability? He says, well, yeah, sure. To an infinitely intelligent being who knew the laws of nature and knew the exact disposition of everything at a certain time and could do the calculation, you know, everything, you know, would be before its eyes, and past and future would be revealed to it. But that's not us. We're always infinitely far from that. And we need a science of probability because we're nowhere near that state of complete knowledge. So Laplace's demon wouldn't need, according to Laplace, the being that we now call Laplace's demon wouldn't need a science of probability. And I think according to Maxwell, you know, the being we now call Maxwell's demon wouldn't need science of thermodynamics, or, you know, we get track of everything. Okay.
Am I allowed to?
Yeah, please. Yes.
It's very curious also that there's a third being, demon, which is sometimes called the Loschmied demon.
So which team?
The Loschmied.
The Loschmied.
Oh, okay.
Because Loschmied, somewhat later after Maxwell, but apparently independently, also came up with a kind of argument which is closely related. So Loschmied imagined that we had some superior intelligence who knew all the positions and velocities of the molecules in the gas and could calculate the deterministic evolution of the gas some points later. So initially, say the two, let's say we've got two kinds of molecules in the gas, and we have them interdiffused, and they reach the state of thermal equilibrium. Now, the superior intelligence knew of the initial state, he calculated the final state, and now he designs a diaphragm, a screen in the middle, which has little holes exactly where the particles of the first kind were, but not where all the particles of the second. And so he enters that partition in the gas, and then he's able to separate again the particles of the first kind and the second kind. So the goal is exactly the same as in Maxwell, trying to undo the irreversible mixing. The difference is that Loschmied relies on the deterministic evolution of the gas and only the information about the initial state.
And what's the point that Loschmied wants to draw from this? Because I remember trying to read that, and my German totally sucks, and it didn't seem to me that he was clearly saying something like Maxwell is, that, you know, here's a limitation on the second law of thermodynamics. But what's the moral that he draws, that Loschmied draws from this?
He also draws I think the conclusion. He is very much against. He thinks of the second law of thermodynamics as a terroristic nimbus.
Okay.
That we, because it threatens the heat death and the running down of the universe.
Okay, but that sounds like he doesn't like it, but does he also think it's false?
Oh.
Because, I mean, there's a lot of people in the 19th century who were sort of lamenting the inevitable heat death of the universe, but thought it was inevitable. You know?
No, so well, I let me not try to say. I mean, I would have to look it up again to see what more to be more certain. But what I find striking is that Loschmidt's demon is just like Laplace's in the sense that he only has superior intelligence.
Right, but not superior.
Maxwell's demon does not rely in any clear sense on determinism.
Right.
It also, of course, doesn't necessarily rely on time reversal invariance. But what he does rely on is observational and manipulative capabilities of demon. So he always refers to those two things. He has to be fine-sighted and neat-fingered. So it's not a matter of pure intelligence. It's
right. Yes.
the ability to intervene in the system and not having superior knowledge. He's
a hands-on demon, right?
He's hands-on, and he's very observant.
Yeah. Right.
But he doesn't have a superior brain.
Right. But Loschmidt's demon is a pure rationalist demon.
On the reverse, because he's got to know the initial state exactly, so
he doesn't have to know the initial state. He just watches.
Right.
The Loschmidt demon?
No. The Loschmidt.
Yeah, the Maxwell demon has it.
How does he get to know that if he isn't, fine-sighted at least?
He's fine-sighted, but not fine-fingered.
Right.
Well, that at least, but he's more godlike.
He's more like Laplace's demon. Yeah. Just a quick comment about the reversibility. On that letter to Tate that I quoted from earlier, which is the earliest appearance of the demon, Tate wrote on the margin, very good. Another way to show this is to reverse all the velocities and preside over the subsequent entropy decreasing evolution. And that's the earliest instance of that reversibility argument that I know of.
You also, I read that Loschmidt text recently, but I just don't remember, did he have a screen with holes or was he just reflecting stuff back? I just don't remember the details anymore. Do you remember?
No, I have. You probably read it more recently than I did.
It doesn't mean I remember anything reliably, but I had a feeling he was just going to sort of put little things that would bounce things. He would just deflect each molecule individually. And
I wouldn't know, but I think it doesn't.
It doesn't
really matter. I mean, it's obvious that either by plugging holes or by reflecting, you will have a means of separating the two.
Well, the holes strike me as a little more difficult because I know I can always sort of target a particular molecule and put something in there just the moment when I need it. If I'm putting a screen down, there are mutual consistency conditions, so that so that's what I was trying to figure out. But,
Josh, you've been patient.
Another thing I wanted to mention, but perhaps you can come back to that, but it is true, of course, that for Maxwell, the word probabilistic and the word statistical have entirely different meanings.
Yeah, I wasn't planning on saying that today. If you want details on that, I will refer you to my paper. What's it called? Statistical Mechanics and Thermodynamics and Maxwellian View. So, I don't want. Yeah, so I mean that's the reason for, when he says the second law. Well, okay, when he says the second law of thermodynamics has only statistical certainty, what he means is it's one of those statistical statistical regularities which are reliable when you're dealing with, say, a population in the large rather than individual. I mean that was Quetelet was one of the people that made a big deal of that. That even though it's really hard to, and this was a couple of real discussion in the 19th century. Even though it's really hard to predict when an individual person will die, if you want to know what of a large population, what proportion of the population will die in a given year, you can be more certain about that. And Maxwell actually said in a lecture to the British Academy of Sciences, he says, yeah, we physicists have taken over the methods from the statisticians on this. Josh, you've been patient.
So the picture I have, according to Maxwell, thermodynamics and statistical mechanics only make sense for, well, it's only useful and kind of makes sense for us to have it for beings.
I would say only makes sense, right?
Right.
Because can you formulate the basic concepts without this means relative distinction?
Right. So now, do you think that when we're kind of thinking about how it is that we should interpret statistical mechanics, that this can be used as a means, well, any interpretation of statistical mechanics that doesn't take seriously this kind of means relative distinction is one that we can just chuck out?
That's a stronger way of putting it than I would be inclined to do so. But no, I mean, just check out. I mean, I actually think that this is that Maxwell's right about this, and if you look carefully enough, everyone is at least implicitly evoking these kinds of distinctions. Like and when you start looking for them, you find them, right? You know, in the Gibbs thing, this, you know, finding a statistical mechanical analog of entropy starts out with identifying certain parameters in the Hamiltonian, which are going to, you know, changes of which represent the work terms. The Boltzmann approach, you know, starts with partitioning the phase space into macrostates. Well, macrostates are supposed to be the state, you know, states that we can distinguish by macroscopic means, and you'll get, you know, different Boltzmann entropies for different partitions of the phase space into macrostates. Okay, so yeah, it seems to me unavoidable. Yeah, there.
Just on that, there seems to me a relevant distinction between the various kinds of demons that we've mentioned.
Right. Okay.
That is, it seems to me right that that say a Maxwellian demon or a Lautschmidt demon won't have any use for thermodynamics. But that is, won't have any use for a distinction between heat and work. But there's an important distinction between either of those and something like a Laplacian demon, who can do this with the whole universe. Okay, if they can do this with any individual system, it's still not going to follow. Nothing of, you know. It's not going to follow. It's not going to be apparent to them that there are regularities about the frequency with which macroscopically similar systems assume the same microstates. Okay, that is, they would, for demons like that, there'll still be something in statistical mechanics that they don't know about the world if they don't have statistical mechanics. For a Laplacian demon who's doing this with the universe as a whole, none of this is going to make any difference, and all that's going to be relevant to him are the microdynamical laws.
Okay. Say that first thing again.
So here's the deal. I take it that one of the empirical claims that statistical mechanics makes, okay, I mean, I'm not saying this carefully, and I promised to talk about the interpretation of probabilities last time, and I didn't do it, but I'll do it a little bit on Friday. But very crudely speaking, okay, one of the consequences of statistical mechanics is a claim about, given an actual ensemble of macroscopically similar systems, what's the frequency with which you'll find this exact microstate or microstate within this region among these systems? Okay, something like a Maxwellian demon who just deals with the microstate of systems individually, system by system, when he encounters one. Okay. Is still, it seems to me, going to benefit from something in statistical mechanics which is a claim about the frequencies with which such microstates obtain, okay? Or at least, I don't know if he'll benefit from it, because any system he encounters, he can just look and see what the microstate is. But I mean, there would be something that would be true about the world that you wouldn't know, that you don't get just from the microdynamical equations of motion.
Yes, there is something that's true about the world that you don't get just from the microdynamical equations of motion. And I think the thing that
whereas for a Laplacian demon, he just wouldn't care. He's doing the whole thing.
I think that the thing that you're putting your finger on is that, okay, suppose the demon can indeed separate these gases. It remains true that in the absence of such manipulations, these things occur spontaneously, rarely, if at all.
Exactly right.
And so,
good. That's a good way to put it. Right.
And that's an important fact about the world.
That's right. And that's a fact that's not. And if he had just thrown away statistical mechanics, he wouldn't have that. Right.
Okay, I accept that amendment. Right. Yeah, and that's important. And okay, that fact. I just want. Let me just flag something, because this is going to be true of what I'm going to say after the break. That fact, which is important, there is this distinction between the sorts of things that tend to happen in the absence of our manipulations and the sorts of things that don't.
Right.
And they're statistical regularities, because it's going to happen rarely, if at all, that these things are. I'm not going to say anything about that, because I don't know what to say. But the fact that I don't say anything about it doesn't mean I don't think it's true, important, and something that needs to be said about. Right? Yeah. Okay.
And just, given we're talking a lot about Maxwell View, I feel there's some value in flagging the fact that the framework here, and the Maxwell's position, but also the framework that protects it seriously here, is committing to the fact that the restrictions on building the demon are mere technology. I do think it's worth being aware that has been, for at least the last several decades, a pretty strong consensus in physics that there are much stronger bars of that kind grounded in information theory and the entropy cost of rate. And that might very well be, as John's argued, that there is something wrong with those arguments. But I think we shouldn't pass over in silence, or to recognise the idea that you can build, the restriction of building a demon are merely technological is very heterodox in conventional physics.
Well, we're going to get a whole morning of it tomorrow, so don't worry, you'll be happy. Or unhappy, as the case may be.
This is of interest. Is that if you think that one of the goals of statistical mechanics is to recover something like the second law of thermodynamics, it matters which version of the second law is the goal. And on this kind of view, we suggest that the sort of thing we should be aiming for is something like, if there's some limited set of variables, macro variables, which are the ones that I can gain information about from my measurements, and I can manipulate, or actually those could be different sets, I suppose, then I cannot reliably decrease entropy as defined with respect to those variables. If you put it that way, that has the flavor of something that maybe on minimal background assumptions could be turned into a theorem. I haven't been able to work that out, but then it would become essentially analytically true. Though I'm pretty something like measure preservation of the dynamics, which is a physical fact, has to come in there, and something like some assumptions about the sorts of things that occur in the absence of your manipulations are going to have to be in there.
Right.
So modulo certain background assumptions, you think this would help turn into a theorem. And when you put it this way, it's reminiscent of what E.T. James calls the correct statement of the second law of thermodynamics. One of the things that proposed talking about, given if there were more time, was something about James. Just for those of you who don't know, E.T. James has a particular way of thinking about statistical mechanics. He thinks of the probabilities as purely epistemic, but he's an objective Bayesian in the sense that he thinks that there is a strong principle that constrains the credences of rational agents, which is, he calls the principle of maximum entropy, which is basically choose as your credence function the one that maximizes this subject to the constraint that gives the right values to the things that you know the values of. And Jaynes in two places presents what he calls an almost unbelievably short derivation of the second law of thermodynamics. And there's some literature on that trying to understand exactly what the argument it is, because if there is a correct argument there, it's elliptical, and it's not clear what exactly how the argument is supposed to work. But I mean, part of the literature that I think has been hampered by people think that he's trying to produce something stronger than he is, but he this is Jaynes's view. The correct statement of the second law is not that an entropy decrease is impossible in principle or even improbable. That rather it cannot be achieved reproducibly by manipulating the macro variables that we've chosen to define our macro state. And I think that that's what he thinks he's proving in this unbelievably short proof of the second law. But I've been unable to reconstruct an actual correct proof of even that from what Jaynes says. But it seems to me that modulo assumptions about the dynamics, which primarily will be that they preserve their volume preserved. And there has to be some kind of assumption, as David pointed, about the sorts of things that happen in the absence of
our that's a
populations.
huge gap
Right?
between, there's a huge gap between what you just said and Jaynes, it seems to me.
Yes! Yeah.
Jaynes thinks there doesn't need to be this additional thing. I mean, he's in a sort of a priorist, what I was calling a priorist tradition relative to this additional thing.
Absolutely. And so, I mean, the question is, I don't think that Jaynes has succeeded in his goal. And so the question is, of the things that Jaynes leaves, what would you have to put in order to make this actually work? Yeah, I mean, Jaynes, I think, vastly overstates what he's achieved. Yeah. Oh, okay. All right. Okay. All right. Now I want to talk about something that's come up several times and has been put aside. How are we to think about these probabilities in statistical mechanics? One thing that I think should be said right at the outset in any discussion, serious discussion of probability, is one thing that I think is incontroversial, and ignoring this, ought to be uncontroversial, incontrovertible. And ignoring this fact has been had a pernicious influence on the discussion of philosophy of probability. The word probability is not univocal. There's more than one distinct sense of probability. There's a lovely book by Ian Hacking called The Emergence of Probability, where he goes back through the history of discussions and demonstrates that even from early days, these two senses were there. And occasionally you find people explicitly distinguishing them, but even when you don't, they're there. Two senses, and I don't claim that these are the only senses. One is it is an epistemic sense. Has to do with the degree of beliefs of a possibly idealized agent. So I'm going to call those credences. Hacking calls those the epistemic sense of probability. And then there's another sense, which Hacking calls the aleatory sense. It's a sense in which we attribute probabilities to certain physical setups, like the roll of a die or the toss of a coin, which is why he calls it the aleatory sense. And these are meant to be features of the physical world, setup. And actually, then maybe these things that are supposed to be features of the world need to be divided into ones that we think are basic in the physical law. On some interpretations of quantum mechanics, some events are objectively chancy events, that the laws of nature themselves are chancy, and even Laplace's demon, who knew the present state of the world in all its detail and knew the laws of nature, would not be able to prevision the exact details of the future. Then there's a question about whether there's a physical objective notion that fits within a deterministic framework, and there's been quite a bit of literature on that. And it's that latter question that got me thinking along these lines. It comes up in connection with Maxwellian mechanics, which is a alternative to standard quantum mechanics that supplements the wave function with particle positions and everything. It has deterministic laws of motion for everything. But nevertheless, in the context of such a theory, we want to be able to talk about the probability of outcomes of experiments. And so I was thinking about that. But also, in the context of classical statistical mechanics, where at least prima facie we can ignore quantum probabilities. I say prima facie because that has been disputed. And when you guys edit this, you have to edit this following out, because this doesn't go in the room. I confess I have an intuition. I have an intuition that the classical statistical mechanics ought to be an autonomous science and not have to borrow its probabilities from quantum mechanics, but I confess it's really nothing stronger than an intuition. Okay. Don't tell anyone.
Wait, does the end interpretation count as deterministic?
It counts as deterministic from this point of view, and then it has. Oh, let's not get into it. Yeah, because you would say that we finally understand what probability is, and I would say on your version of Everett we have something that plays the role of probabilities, but aren't probabilities, and let's just not do that today. Okay. Surely we can organize one Everett free. Because what happens, I mean, my advisor, Abner Shimoni, once said, discussion of the Everett interpretation is like a gas that expands to fill up whatever.
No, look, you're expanding the Everett.
Okay, all right. Okay, all right. You're not going to. Okay, all right, good. Okay. So, just a reminder of what Joseph was saying yesterday about the Gibbsian approach is you start with a phase space, which can be given the specification of all the position and momentum of all the particles. And then there's certain standard equilibrium distributions. Basically, they're constant on energy surfaces. There is a sense in which they're as uniform as possible, subject to certain macroscopic constraints. Okay, and textbooks will introduce these. And if you look at the way textbooks introduce probabilities into this mechanics, there's something puzzling about them. And I'm thinking in particular of a certain textbook tradition that goes, I think, ultimately back to Richard Tolman's 1938 classics text on statistical mechanics. Looking at textbooks, it can be an actually interesting thing because textbooks are primarily written by consulting other textbooks. Someone learns the subject from some text. They go on, they start teaching courses on that. There's new developments, they become unsatisfied with the way the existing textbooks are, and then they end up having to write their own. But the book that they use has been heavily influenced by their own education. So there are like sentences and phrases and almost whole paragraphs that you can sort of trace from Tolman that you can sort of trace through the textbook tradition. And I mean, that's not just true of that, that's just true of many very influential textbooks. Right? So, I mean, he also was talking about the influence of Planck's text on thermodynamics. Okay, so what a lot of these books say is that why introduce probabilities in the first place? Well, typically they say something like, well, these are systems of a huge amount of degrees of freedom. We don't know the exact microstate. Even if we did, we wouldn't be able to follow it through its evolution. And even if we could write down the exact equations of motion, we couldn't solve them. And even if we could solve them, if someone hands you like, a planet-sized USB key with the exact solution on it, it wouldn't be much good, right? Because what you want to know is the certain facts about macro variables. So they're introduced because of our ignorance of the precise state system. And there's often a sort of side reference to a principle of indifference. Tolman himself used the phrase the postulate or assumption of uniform a priori probabilities, and that suggests an indication of a principle of indifference. But he actually argues for the reasonableness of it on physical grounds, and then says ultimately the postulate is to be justified by its empirical success. So we actually make predictions on the basis of these probabilities. What you do is, for large systems at least, you want to know the equilibrium value of various parameters are. You write down a probability distribution like this. Then you calculate the expectation value with respect to that probability distribution and say, well, that's the value we're going to find because you've argued that you have a large system, that the variance in that quantity is going to be small, and so the actual value is very probably going to be close to the expectation value. But we do more than that, as John emphasized. We also calculate probability distributions for fluctuations around equilibrium values, and that all seems to work very well. If you think about that, that's puzzling. That something introduced on the basis of ignorance, that suggests an epistemic reading of these probabilities, is something that I can use to generate testable predictions about. This suggests an epistemic reading of the probabilities, but hey, if I want to know about David Albert's state of belief, I'm not going to go and do experiments on a box of gas over there. So there's something puzzling about that. Another puzzle is that if you took these equilibrium probability distributions seriously as the correct, in some sense, either objective chance or epistemic or what have you, as the correct probabilities of a state of a system that just recently relaxed to equilibrium, then as David made the point very well yesterday, that can't possibly be right. They can't possibly be, they're just wrong because, and one way to see that they're wrong is that they make these disastrous retrodictions. And basically, I mean, we talked about this yesterday, but I mean, basically the point is that, if I can do that free expansion thing again, example, box between here, and then it diffuses, and let's say this is an isolated system. The state of the system is, a state that can come from this as an initial state. And if I apply the standard equilibrium distribution to the state later, this, earlier states in this class get vanishingly small probability. So something's going wrong. And what I want to do is try to give an account of probabilities in statistical mechanics that makes sense of our use of them. And the desiderata are that they actually do accommodate the idea that they reflect interdifferential of microstates. But it also makes sense of empirical verification of probabilistic postulates. And okay, if you're saying, okay, that's just inconsistent, I could go, might as well stop now. Wait. Also explains the use of these equilibrium probabilities. How can we get? Actually, I should say it explains why we should use these equilibrium probabilities, even though we think they're wrong, and why should these equilibrium probabilities be uniform in phase space variables rather than some other variables? Like people who invoke a principle of indifference very often gloss over the well-known fact that something that's uniform in one set of variables isn't going to be uniform in another set of variables, and it requires a choice. Is it an actual choice? Well, what makes it an actual choice? And basically what I say is that the familiar dichotomy between objective senses of probability and epistemic sense of probability isn't exhaustive. That what I want to do is introduce a new concept which is a hybrid that requires both epistemic considerations and physical considerations to be characterized. Yeah?
Okay, there are two things. One is that the option of objective chances in a setup in which, okay, this is disputable, but in which we are in the beginning assuming that deterministic laws are applying.
Yeah.
I know there are the deterministic accounts of objective chances, but I mean, you should have to stick to these new versions of deterministic objective chances to accept something like that. That exists.
Yeah, I mean, those who claim, who want to say, I have a notion of objective chance that makes sense in the deterministic context. And one of the things they want to say is, typically, is, and this makes sense of probabilities in classical statistical mechanics. Yeah. So, but I don't want to talk. I don't want to talk about that. Okay. Because that's not what I'm going to be doing. Right.
Okay. Well, then by the other hand, I don't see really that there is something to be worried about in the epistemic interpretation. One of the things when you said that there is this empirical predictions that it makes, and then you have to be like a big pattern because of that. Because I suppose that in any case when you make an epistemic probability because you think you have ignorance of some hidden variable or something like that. I don't know, in quantum mechanics there was people thinking, okay, maybe there's some hidden variable and the probabilities are epistemic. But of course these people, I don't know if Bohmians are in this line of thought. But in any case, the probabilities of course were epistemic, but were
I would say
fitting with the predictions.
I would say that classical statistical mechanics and Bohmian mechanics are pretty much in the same boat in this. And actually, the line of thinking that I want to present, I actually originally started thinking on these lines in connection with thinking about Bohmian mechanics.
But I take it that the thing that Wayne is calling puzzling is something like how can some claims about what this system is going to do, or probably going to do, or anything like that, follow from a statement like I have no clue what state it's in. That's what I take it Wayne is presenting as the puzzle that he wants to address.
Yeah, and I was but you convinced me more or less that when you have situations of absolute ignorance, then okay, it's changed to assign probabilities. But is this, I mean, in these cases,
Well,
don't we have
it's not restricted to situations where I get to say I have no clue. Like situations where I have a determinate credence. You know, predict. You know, if I want to, if I wanted there to make empirical claims about David Albert's credences and test these claims about David Albert's credences, surely the best thing to do is either ask David, or if I think that people aren't reliable reporters about credences, do some kind of tests on David to figure out what David believes. Doing an experiment on a box of gas seems like a lousy way to find out about anybody's credences.
But quick visualization, you want to build a bridge, so you want to use some strong steel, and so you go to a condensed matter physicist. He says, "Here's some really strong steel," and you take it away. And he says, "But you just need to understand, when I say it's really strong steel, that's actually an indirect way of making a comment about my credence across microstates. I'm not telling you anything directly about the steel."
Yeah, we want them to
right,
yeah, exactly. We want these statements to be to at least be, in some sense, statements about the physical systems and not statements about our credences. I think it'll become clearer as I go on. So I can continue. All right. Okay. Now, one thing that becomes kind of puzzling if you don't distinguish between credence and chance is what happens when I'm flipping a coin and trying to learn about its bias, and everything becomes totally clear if I just distinguish between chance and credence, because credence are degrees of belief and chance are supposed to be features of physical systems or setups. Then values of chances are among the things I can have credences about. And basically I'm following David Lewis here in his Subjectivist Guide to Objective of Chance. And the way that works is, if I want to know, if I have a coin in my pocket, and I want to know is it biased towards heads or not, what am I going to do?
Flip.
Yeah, lots and lots of times, right? And compile the statistics, and if I flip it lots and lots of times and it comes roughly roughly heads and tails, then I'd say, okay, it's probably close. If it has any bias, it's a small bias. And I just want to talk about how that works.
What do you mean by chances in the context of statistical mechanics?
I'm stepping. I haven't yet said what I mean by chance in the statistical mechanics. I want to step aside and say,
you step back and talk about.
I'm stepping back, yeah.
Coins.
Yeah, talking about coins, and set aside any worries you have about a coin being a deterministic system, and just treat it as coin is standing in here for chance setup. Right. So this is if you want, is a quantum coin, or whatever you think might, or okay, so I have a coin that says, has a bias, lambda, saying it's a probability on each toss of lambda of getting heads. And I want to know what that is. Well, I might start out with some kind of credences about that. And if I think all biases, if I regard all biases as equally likely, then my credences about the chance, my credences about that by chance we represented by a flat density function, and that just means that my credence that it's in any given interval is equal to area under that interval. If I think that because of my experience of the world, I think most coins are, it is highly likely that this is something close to a fair coin, but I know there's actually some trick coins out there. It might be something like that. But I'm assuming they can be represented by some kind of density function. So this is a credence density function, my credence about the chance of heads on every toss. Does everyone understand the concept? What I'm going to do is, so that's what I said. My credence that lambda is in delta is given by the area of under that function over delta. Okay. So suppose I flip the coin a whole bunch of times and I get some result. And I think when I prepared this slide, I actually, did flip a coin. So that's the result I got. So that has, how many heads in it? 3, okay. How many tails has it got? 7, okay, 7 heads and 3 tails. And for any value of lambda, there's going to be a certain chance of getting this result. In fact, we can calculate. What's the chance of getting precisely this result if the chance of heads on each toss is lambda? Well, what's the chance of getting tails on the first toss? 1 minus lambda. What's the chance of getting tails on the first and second tosses?
Well, that's not potatoes, you want tails and heads.
Oh, tails and heads. Okay, I'm sorry. I forgot what. What's the chance of getting tails on the... That's why Cassie was looking puzzled. What's the chance of getting tails on the first one and heads on the second one?
You have to specify whether they're independent.
Yes. Yes. Implicitly assume they're independent. They make the assumption explicitly. It's explicit. Okay. Yeah. Okay, so you're certain that they're independent. Yeah.
1 minus lambda times lambda.
Right, yeah. So it's going to be 1 minus lambda times lambda times lambda times 1 minus lambda, etc. So it's going to be 1 minus lambda with the exponent 7 and lambda times lambda with the exponent 3. So whatever m and n is going to be, I have no idea why the lambda turned into an x, but I would check to be a lambda. It's going to be that. And the interesting thing about this function is that if you ask where does it have its maximum, it has its maximum at the observed relative frequency of heads. So this function is considered as a function of x, takes its maximum at the point m over m plus n, and it's a more sharply peaked function the larger the number of tosses. Now, what I want to do is update my credences by conditionalizing on the result. Does everyone know what that means? Who doesn't know what that means? Okay, what's it mean? Someone who does know what it means. What am I doing?
What was the question?
I'm going to up my credences by conditionalizing on this evidence.
Yeah, I don't know what it means.
Okay, what I'm going to do is I'm going to apply, I say Bayes' theorem. Do we know what this means? I apply Bayes' theorem and say my new credence is going to be my old conditional credence on the result, which is going to be my credence conditional on a hypothesis. And now what I'm going to do is I'm actually going to have a continuous range of hypotheses I'm considering the form, chance of heads equals lambda. And that means that what I'm actually going to do is have a likelihood function here, which is the likelihood, chance of getting this result conditional on the hypothesis that the chance of heads is lambda. And basically what this conditionalizing does is it multiplies my old credence density function by this likelihood function, and then you normalize it so it's normalized to 1. So the new credence density function is proportional to this likelihood function times the old one. And the proportionality is just normalization constant. Okay, so what do I put in here? What's the, what's the chance of getting this, or actually what, I've been guilty of eliding. This should, I'm calling this likelihood function a chance, but really what needs to go is a conditional credence function. So, what should this be? What should my credence in getting this result conditional on the supposition that the chance of heads is lambda?
Identity?
What's that?
Identity?
Well, what's identity? One?
Equals. Sorry, just equals. Sorry, equals the likelihood function.
Yeah, right, yeah. They should be equal, and the claim that they should be equal is called the principal, yeah. If you read David Lewis's Subjective Guide to Objective Chance, Subjectivist Guide to Objective Chance, he identifies what he calls the principle that says it's meant to be a constraint on reasonable credences that your credence in a given event, a conditional on the supposition that the chance of that event is x, and then the admissible information should be simply equal to x. There's an unfortunate tendency to gloss that as the prescription to set your credence equal to the chance, and that is emphatically not what it says. It doesn't tell you what your credence should be. It tells you what your conditional credence should be. It tells you what your conditional credence, conditional on supposition of the chance should be. And that's important because typically we won't be, in the cases where the principle is actually doing a lot of work, is cases like this where we're trying to gain evidence about chances. And we will be uncertain what the chance is. So I'll have my credence in a given thing. My credence in some proposition A is going to be an average of my conditional credence in A conditional on the supposition that the chance is lambda times my credence density is lambda, and where this is a delta function, I'm certain I know what the chances are. Then we have equality. But really, where the principle is doing work is when it's turning evidence like this, into evidence about chances. Poisson, in his book on probability, has a nice discussion of the distinction between what he calls probability, which is the epistemic view, and chance. And he says, there will be lots of cases where we are actually certain that our degree of belief is not equal to chance. A good example is that I might have a coin where I think it's either biased 2-to-1 in favor of heads or biased 2-to-1 in favor of tails. What's my going to be degree of belief in heads in that case, assuming that my credence is satisfied the principle? 1/2. But I'm certain that the chance of heads is not 1/2. Okay. All right. Okay.
Can I just check?
Yeah.
So, I know this is a stupid question. Where is Bayes' theorem coming in? Just in the
Bayes' theorem.
In setting it as proportional, that's being motivated by Bayes' theorem.
If you plug Bayes' theorem into the case where you've got a continuous continuous range of hypotheses, and you want a new density function, basically what you do is here I'm just considering one hypothesis, and I start with my old credence and multiply it by the likelihood. And in this case where you have a continuous range Bayes' theorem tells you that you do this, your new credence density function is the old one multiplied by the likelihood function. Yeah.
I'm intrigued to hear that, because I haven't read Poisson in detail, but all of the other authors from that tradition, from Myrvold to Laplace to Rotman, also the followers and pupils of Laplace, insist that chance does not exist.
Yeah, Poisson does not.
Okay.
Yeah, and in fact, I would like to go into the history of this a bit more, because you do find people distinguishing between these two senses of probability, and then it drops out in the 19th century. Okay. And then what happens is that the idea, there's still this idea that there's an objective notion of probability, but that becomes a frequency conception. To the extent that when you get to the early 20th century and you have people like Definetti and Savage arguing for a subjectivist view, single case objective chance isn't even a candidate on the table for refutation.
Yeah.
And in 1955 or whatever, Popper comes up as, I have this new idea that no one's ever thought of before, single case objective chance, which I call propensity. But it was an old idea that somehow got dropped out. And my historical conjecture, and I haven't really looked at it in detail, is it's really thinking about determinism and worrying about how there could be chance in a deterministic world that led to that dropping out. Even though people earlier were thinking
it depends. In case of Laplace, it's certainly determinism. This whole argument for the demon is only meant to fortify the argument that therefore probability must be epistemic. In the case of Lemaitre and earlier authors, it's very often not so much the determinism of physics, but the omniscience of God. That I mean, if something is really, if there's a real chance, that would somehow imply that even God hasn't made up his mind, and that's sort of a no-go area. So therefore, we declare that chances do not exist.
Right, good. All right. So, if my credence is satisfied the principal, what I'm going to do is, as I wrote over there, I'm going to update my credence density function by the likelihood function. And what it does, assuming that your prior credence density function isn't 0 in some interval around the observed relative frequency, because you can multiply 0 by anything and still get 0. What it's going to do is it's going to tend to boost credences near the observed relative frequency and suppress others. And so if you do this enough, any density function that's non-zero everywhere is going to, given enough evidence, end up sharply peaked around the observed relative frequency. Okay. All right. Okay. That was a digression. Now I'm going back to statistical mechanics. I'm going back to the example of free expansion of the gas. Because I want to know, what I want to do is suggest a notion of probability that combines both epistemic and physical consideration. So, here it is. Suppose Bob has some credence function that represents his credences about the state of the gas at time 0. And you pull it out and let it go. There is going to be some credence function which is a result of applying the actual evolution of that gas to P0 in the way that Jos told us about yesterday. If you want to know the probability of it being in a certain region at T1, that's P0 applied to you ask, okay, which things evolve into, which points in phase space evolve into that region from T0 to T1, and you apply P0 to that set. And so there's going to be a probability function that results from P0 by the laws of O2. Now, is that going to be represent Bob's credences about the state of the gas at time 1? Yes or no?
Yes.
How many say yes?
It's obviously a trick question.
Sure. It's not meant to be a trick question. How many say no?
So just ask it again. Is it? What do we know about Bob? Has Bob read David Lewis, for example?
What's that?
Has Bob read David Lewis?
Bob's read David Lewis, yeah.
And Bob knows the microdynamical equations of motion.
Okay, okay, yeah. So that's the key thing.
Oh.
Yeah, it does depend on what we know about Bob. If Bob knows the microdynamical equations of motion and can do the calculation,
Right.
then coherence requires that to be there.
Right.
Okay, first of all, we're not going to know the exact dynamics. Secondly, even if we did, Lanford can only do that calculation for incredibly small time. It's an enormously difficult calculation to do because because this probability distribution, this P1 will not be the uniform distribution over this set of states now accessible. As was pointed out yesterday, it's going to be, it's going to, if this is our phase space, and say this is the enormously small region of phase space. This is the phase space for the gas, including all the volume of that whole box accessible to it. It's going to be an enormously small region of that phase space that has all the molecules in all the molecules in that side of the box. So small that I can't draw it if it's a large number of molecules. And the evolution is going to preserve volume. So what it's going to do is, this thing is going to go to something that's, people have tried to draw this. It's going to be some, enormously fibrillated thing that's, kind of spread out all over the phase space, but it's still going to have the same small volume. It's going to be this god-awful complicated thing. So, even if Bob knew. So if Bob were Laplace's demon, the answer is yes. P1 would be the result of P1 would be his new credence. But if he's not, if he's anything remotely like being an agent if it's an agent with anything remotely like the cognitive and calculational abilities of a human being, well, one, we're not going to know the precise dynamics down to the last detail. Very small differences in the Hamiltonian are going to make differences of this. Two, he couldn't do the calculation. And three, he probably couldn't write down this function and it's all in detail on anything that you could actually hand to Bob.
I think that's it.
What's that? Did I say probably? Okay. Right, yeah. The IBM people are working towards a place where you can have all the movies ever made on a little chip, but you probably have to take a galaxy of those things to write down this thing. Okay, so if Bob has any serious cognitive limitations, the answer is no. P1 will not be that. Okay. What's Statistical Mechanics? What's the credence he would have if he knew the laws and could do the calculations? But he can't, so it's not. Okay. imagine there is a Laplacian demon who knows Bob's. This Laplacian demon doesn't necessarily know the exact microstate of the gas. He doesn't care about that. But Bob can tell the Laplacian demon his initial credence state, and the Laplacian demon does know the exact microdynamics and can do the calculation. And so that's a useful thing to Bob to know, because what the Laplacian demon can do is tell him what his credence ought to be if he were able to fully exploit the possible knowledge about the evolution of the gas. But as I said, the Laplacian demon can't just give Bob the answer to the question. He couldn't write it down on anything that he could actually hand to Bob without killing him. And it wouldn't be much good to Bob even if it did. But what the Laplacian demon says, okay, I can't give you the full answer to what this P1 is, but I can ask certain questions. And Bob says, because really all I want to know is probabilities for results of experiments that I can do. And so the Laplacian, so Bob starts asking a question. He says, I want to do this experiment, and the demon says, okay, here's the probability distribution for the results of that experiment. And Bob says, I want to do the experiment, and the demon says, oh wait, I can save you some time. Use the microcanonical distribution. It's going to give you the answers to all those questions within the limits of tolerance that beings like you care about. It's going to it's very different from this P1, but it's actually sort of a side effect of how complicated this P1 is, that the answers to certain questions are simple. That if you want to know what's the probability that the state of the system is in a region A? Well, that's going to be the probability assigned to A divided by the integral of the whole thing over space. And if this thing is all kind of finely fibrillated all over about, that's going to be actually close to the actual phase space volume of A. Probably, and this is a plausible conjecture, that the demon can actually do the same thing for the credences of any agent, provided the credence of that P naught for that agent isn't too weird. Bob and Alice don't have to have exactly the same credences about the state of the gas at time 0 for those credence functions to have this property that the demon can basically answer questions by saying use the microcanonical ensemble. Yeah.
You're going to say, the demon says use the microcanonical distribution.
Yeah, sure.
You can say a little bit more about how that gets into the calculation. That gives Bob his likelihood.
That gives Bob what his credence would be if he knew the. So this P1 is what Bob's credence would be if he knew the precise microdynamics and could do the calculation.
Right.
That's what it's doing.
What's doing?
That's the question that the Laplacian demon is answering by saying use the microcanonical ensemble. But no, that's what I'm not saying that the microcanonical ensemble represents the credence function, what his credence function over the microstate would be. What I'm saying is it gives the same answers to the sorts of questions that Bob is asking the oracle. Basically, questions about probabilities of results of feasible measurements.
Going forward in time.
Going forward, I'm going to come back to that. Yeah, I'm going to come back to that. Yeah. So any sort of question about what's going on? And so if the dynamics are the right sort, what they're going to do is, and if the dynamics are the right sort, and if the questions that we're asking about at time 1 are of the right sort, then what's going to happen is the dynamics are going to turn a wide variety of credence functions about the initial state into credence functions that lead to effectively the same answer about probabilities of results of feasible measurements.
Sorry to be thick here, but just, so in effect, the Laplacian demon is saying above, forget about all that updating stuff and that, just assume that the system you've got now fits the microcanonical distribution, right? And then get your results that way.
Or
is that what you're saying?
Or use the microcanonical distribution as a surrogate, calculational surrogate for this more complicated thing that I can't give you. And the reason I say
surrogate for P1.
What? Yeah, for P1, yeah. And the transition from P0 to P1 isn't updating.
No, there's no new evidence.
Right, there's no new evidence, right? He's not learning anything new. It's just dynamical evolution. And if he could do the calculation,
you still use Bayes theorem, no?
What's that?
You just use
No.
Bayes theorem.
Don't you use.
But doesn't that become a kind of a transition probability?
No. Okay, yeah, this is confusion off the cover. There's no updating involved because there's no new evidence. If Bob,
but I assume there's a formula that's going to look similar that'll say
the formula is Leibniz's theorem. You take this initial probability distribution and evolve it according to the dynamics. And you get
the formula is Leibniz's equation.
Right. Yeah.
Right.
I'm sorry, Leibniz's equation.
Right.
Leibniz's theorem is the claim that phase space volume is concerned.
Right.
The formula, it's got nothing to do with updating.
Right.
Right. And So I think it's a possible conjecture that for the sorts of systems we're interested in, the dynamics actually do have that feature. And what do I mean by credences of a reasonable agent? I mean, about this vague is, imagine someone. This has to do with the instability of anti-thermodynamic trajectories. So suppose someone said, Alice said, well, my credences about the state of the system are such that I have, I strongly believe that it's going to evolve back into one of those components, in 5 minutes. So how the hell do you know that? That requires very detailed knowledge of the state of the system, because if you perturb the system just slightly, it won't do that, and so you have a density function that's varying, very strongly over short distances. So what I mean is, suppose you have a whole bunch of agents whose P naughts can vary a lot, but all have the feature that there's a bound to how quickly they vary over phase space. Then it's not proven, but it's at least plausible conjecture that those will all evolve into things that give roughly the same results for results of feasible experiment. And there is literature on this kind of thing. There are cases. It's pioneered by Poincaré, and it's rather misleadingly called the method of arbitrary functions. Poincaré considered a roulette-like wheel. You've got, it's divided into a certain number of red and black sectors. You spin it and you let it come to rest. You spin it and you let it come to rest via friction. And let's say, suppose you have a probability distribution over the initial velocity. That evolves according to the law of motion, and that'll depend on exactly how the friction law goes, into a probability distribution over over final conditions. And what things like this do is they tend to spread those probability distributions out. I mean, if you think about it, small, even though it's linear, differences in velocities, lead to linearly to diverging final positions, even linearly. And there's a family of theorems about exactly how that works. And basically they have the flavor of you can express, you write, give me a probability distribution over the omega the initial velocity, that turns into a probability distribution over the final resting place, and these will be red sector, black sector, and what happens is the evolution tends to spread those things out, and you can actually give theorems giving you how close you'll get to equal probability of red and black as a function of how wiggly this initial thing is. So that's the sort of thing I have in mind. These sorts of situations where wide variety of probability distributions over conditions at one time, provided they're not too wiggly, turn into probability distributions that are in some sense as different as they started out with, but nonetheless lead to almost exactly the same probabilities for outcomes of feasible experiments. Yeah?
I just want to check I've got this straight. So once one spells out the meaning of reasonable here, it turns out that it's constraint on reasonable credences that they not be credences about the gas's current state that would imply anti-thermodynamic behavior in the future.
Yeah, the idea I have is that what counts as a reasonable credence about the initial state is that it's roughly constant over areas. I mean, it doesn't vary faster than the sort of information you can have about the state. So
we know this comes from a past which is low entropy. So we know that looking backwards in time, we get to.
Well, okay, yeah, right. So yeah, all right. So okay, what I said, yeah, right, yeah. Actually, what I. Yeah, so yeah, what I said isn't quite right, because I mean I can know that it came from something like this, and I can have something like that, but those wiggles won't be really relevant to future evolution. Yeah. Right. So answer is yeah. Once, and I haven't spelled out what the conditions are. But the conjecture is that there are, and this is a feature both of our judgments about what sorts of credences are reasonable to agents like us, and a feature of the dynamics that those two things will have those features. So yeah, none of this, I don't pretend I've spelled any of this out yet.
It looks a bit like reasonable means consistent with entropy increasing one direction and not the other.
I didn't say that.
No, I know, but it looks like a constraint amounts to something like that because.
Why?
Because it has to be for Bob's credences to count as reasonable. They have to be such that they don't predict forward in time anti-thermodynamic behavior. But he knows that looking backwards in time, you see entropy decreasing towards the past. So doing exactly with that.
Yeah, so I'm going to defer this, but there is a temporal asymmetry in this notion of reasonable credence. It is not a constraint of rationality that my credence function be invariant under velocity reversal. And typically it will not be. Yeah, it won't be. And the reason for that is that there's a temporal asymmetry in the sorts of things I can know about a system. So I guess taking it as an unexplained fact, but nonetheless a fact, that we can have memories and access to the past. I mean, memories and records to the past, of the past. And so we can reasonably believe that this gas was in the left-hand side of the box because I remember it and I have a photograph and I have my lab notebook. But I have no access to its future state other than taking the current state and applying the laws of physics to it. So that, I'm just taking that as a fact about agents like us. And if that's true, then the credence functions of agents like this will not be invariant under velocity. You know, the sorts of things that are reasonable for credence for agents like us will not be invariant under velocity.
But a state on the left-hand side on the left side of the box,
right,
is invariant under velocity.
So suppose my credence at time t0 is invariant under velocity reversal, and it might or might not be, because I might have, you know, I might think it got into that state by okay, I'm going to put it this way. You know, it starts out in this side of the box. And I didn't say anything at all what P0 is. In fact, I didn't say it's microcanonical ensemble aside of P0, right? Because it might not be. Bob might know that it actually evolved from here, and he might have strong reason to believe that whatever its current state is, it's a state whose velocity reversal evolves back into that corner. So, I mean, that's something he could believe about the gas.
Let me not press it,
Okay.
but I was assuming or anticipating that your explanation of what credences are going to be reasonable would somehow involve a level of description, a definition of macroscopic variables, and that Bob would have access to, and that he would only be able to have some credence which was more or less continuous with respect to those things. That would bring us back to sort of Maxwell's limitations. But you don't seem to mention that.
Yeah, I haven't mentioned.
That's what surprises me.
I haven't yet mentioned what I count as reasonable or not. But I mean, here's roughly the idea: is that it certainly can incorporate the sort of information accessible to Bob about the state of the gas, which includes possibly measurements about the past of the gas. And so it can be a constraint on those credences that it could conform to what Bob actually knows about the results of past measurements, but not very too strongly subject to that constraint. Now, E.T. James would say principle of maximum entropy comes in and uniquely constrains Bob's credences to be the one that maximizes entropy relative to the constraint that it gives the right expectation values for the things that Bob knows about the gas. And that can conclude all the results of past measurements. My view is that it seems plausibly that is among the class of reasonable credences, but I don't know an argument that he's uniquely constrained.
Yeah, but the important point, I think, is if you take that step, then Bob's credences might be reasonable with respect to or relative to the kind of level he is employing. The demon's grievances might be relative, might be reasonable with respect to the kind of capabilities and descriptions he
Yes.
has.
Yes.
So there's no objective or unique
Yes.
definition or dichotomy between what is reasonable and what is unreasonable.
Yes.
That would seem to fit with exactly the,
That's it, yes.
the first
that-
part of what you were talking about.
Yeah,
before.
that's exactly right. That's where I'm headed.
Yeah.
That's where I'm headed.
Yeah.
Right, yeah,
Okay.
that's where I'm headed. That's why I said that, you know, the preface of this was, look, you know, let's take Maxwell's view of thermodynamics and ask, you know, what kind of view of probabilities in statistical mechanics fits well with it. So, yeah, absolutely. What counts as reasonable for a given agent is relative to the sorts of information available to that agent. Yeah.
Yeah, and I'm starting to worry about consistency here with this between this take on the past side of it and the initial assumption about complexity. Because my worry is something like this. It sounds like the kind of thing that might be reasonable for Bob might be something like a nice, friendly, smooth distribution conditionalized on some early information. But in closed form, a nice, friendly distribution conditionalized on past information is going to be just as unmanageably complicated, and for the same reasons as the previous candidate was for Bob's future credences. So my credence function isn't allowed to be unmanageably complicated. In other words, if there's some requirement that I know my credence function in closed form, then I don't see how this credence function is legit for Bob.
Yeah.
And if I'm not required to know my credence function in closed form, there's nothing wrong with saying, well, my credence function right now just is, you know, I'll specify it as that credence function would have been evolved.
Here's what I want to say, is that yeah, if you want to spell out the count as all in all its detail, you have to make certain complications that I'm leaving out in this sort of preliminary thing. And really, I mean, I've been speaking as if I think I can attribute determinate credence functions to agents. And really, you know, the kind of Bayesian I am is I think it's better to actually attribute to agents, you know, sets of credence functions that are, you know, the things that are, you know, the agent regards as reasonable given what the agent says. And so, you know, maybe I might not even want to attribute a precise credence function P0 to Bob at state 0. And it doesn't matter as long as everything in that class has this property of evolving to something that gives the same results. Also, you know, Bob, you know, for real systems, you know, we're imagining isolated systems, and you know, what would be Bob's credence conditional on what he knows about the past of the box? Well, you know, he doesn't know the exact dynamics, so it actually should be sort of an average over the various candidates for real dynamics. It's been interacting with the environment that he precisely knows. That average actually could end up being so smeared out it looks an awful lot like a canonical distribution. Right? Yeah. So actually having poo-pooed the standard equilibrium distributions, you know, if you say, okay, there's all this stuff we don't know, and if I believe that it's in the that it's in this little corner at a certain time and it evolves, but I don't know the exact dynamics, my credence actually might be sort of average of the result of evolving over all the possible dynamics, and that actually could be so smeared out that it actually is something like my microconic or canonical distribution.
So you wouldn't be able to talk about my credence conditional on any given form of the manner, but you would be able to talk about that.
Yeah. Okay.
You've had it.
John?
Yeah, maybe, how are you going for time?
we can have a quick question, yeah.
No, I'll leave it going.
Or we can save it for lunchtime. Okay. All right. So what I would say is, when you're in that kind of situation, and it's going to be a very special kind of situation, where you have, however characterized, some set of credences about states of affairs at T0, which are the credences the reasonable agent could have. And I'm not going to say too much about that, too precise at the moment, because there's not much I can say. And the dynamics such that everything in that set evolves into functions that yield roughly the same result of it's the same probability of a result of some measurement A. I want a word for that value, and I don't know a good terminology. Statisticians sometimes call them almost objective probabilities. I've been using the phrase epistemic chance, and my experience is that sounds like it's chance modified by an adjective epistemic, and then what people do is they take what they know to be true of chances and then object to that this conception doesn't have that feature. And and the terminology is meant to gesture toward the fact that in their very characterization you have to invoke both physical and epistemic considerations. If there's any suggestion on their terminology, I'd like to hear it. Yeah.
It was a suggestion. But
a suggestion,
You
yeah.
can do your suggestion. I've got a
Okay, yeah.
question.
Probabilities well adapted to the chances. Well adapted. Is that what you mean? I mean,
well, in a deterministic, I don't want, in a deterministic situation, actually, it's not clear to me that there isn't a chance in this case. I want.
So objectively well adapted probabilities.
Okay, that's good. Yeah. Right. Yeah.
So maybe this is doing exactly what you just told me not to.
Yeah.
By saying this doesn't have a feature that transfers out.
Right.
But it seems like there's like a worry about explanation here. That if we started off with the idea that the microdynamics on their own couldn't explain, don't on their own explain these general thermodynamic phenomena, then it's not clear that just adding a constraint on, like an epistemic constraint, a constraint on reasonableness of agents, is going to put you in a situation where you are able to explain things like why generally in this world ice cubes melt in warm water. Okay.
There's no worry about explanation because there's no explanation. I have not even begun to attempt to answer questions like that.
Right. Yeah. So
I said nothing at all about why it is that ice cubes melt.
Right.
Yeah.
So just this fit with a story where there's no distinctive system mechanical explanation. The one we say when ice cubes melt, or is there going to be some other background story about?
There is absolutely no claim that once I get to the last slide, I will have said everything there is to be said about all the issues in statistical mechanics. And in particular, I will not have said anything about the issue that David flagged earlier, is that still there's this sort of judgment about the sorts of things that things tend to do when we're not manipulating them, that we shouldn't expect them to spontaneously sort themselves out, and certainly what chances are what credences are reasonable for beings like us who know things like that will be credences which are informed by that and attach low probability to things like that. But saying that does nothing at all to begin to explain why that is. So yeah, there's no worry about explanation because there's no explanation.
But there's also maybe like
that's a distinct project.
you might suspect that there's not it's not just that there's no kind of explanation yet, but there's kind of an in-principle reason why there couldn't be, because you just don't have enough materials. You have the microdynamics and then you have some epistemology.
Okay.
Those together are not enough.
Right.
Principles.
Yes. And if I were saying at the end of this, and this is the whole story, and you're not allowed to bring any other resources besides what I've mentioned. Yeah. So I want to say I'm not making grandiose claims. Right. So here's what I would say. In principle, there couldn't be. Well, if someone comes along and gives me that explanation, it seems to me I can just bring it on board. Right. And say, okay, and that's why because I mean, among the things that informs our idea of what sorts of credence or reasonable relations is our experience of the world. And if and if there were there are systems that we know that we can reliably say yes, they're going to be in the presence of an IBM tunneling microscope, atoms can be put into precise configurations, but in the absence of that kind of manipulations, they're going to kind of jiggle around randomly. Just use everything you know about the world in your judgments of what are reasonable credence is for agents. Everything. Yeah.
I was going to suggest introspective probabilities.
Well, here's why they're not intersubjective necessarily. This credence, which so Bob asked the oracle, if I were to evolve my credence about states at time 0 to states of time states at time 1, what would be the probability of the result of this measurement? That answer, the answer the oracle gives, is what I'm going to call this episode chance or something.
That's not actually going to cause.
And it might not be Bob's credence at all. These things might not be the credence of any actual agents. If he doesn't know the answer to that question, it's not his credence. Yeah.
Well, there's a history especially to James's work and the introduction of epistemic probabilities and statistical mechanics. And not of all that debate has been very polite or pretty or useful. But there is a basic worry about what the purpose or virtue of introducing agents and credences in what is usually conceived of as a physical theory would be, and which could be at least sensibly, I think, captured in the worry. Like, what if we want to talk about, say, the early 3 seconds in the early universe and why statistical mechanics there, or you want to talk about gases on some uninhabited planet before there are any humans or intelligent beings at all, with no agents, there's nothing, no criteria of reasonableness we can think of. Would we still infer that gases expand and fill their volumes?
Yeah,
Would we think
very
that
good,
there's
very good.
thermalization in the early universe and so on? And, or, well, what would be your response?
Yeah, very good. I'm very glad you asked that, because you're right. That's something that comes up in this literature any time someone introduces a subjective or epistemic considerations at all. But you asked it a couple hours too late, because you should have asked it in the first talk when I was talking about Maxwell's views of thermodynamics. So someone might say, well, look, you're bringing in, considerations about what agents can and can't do into your formulation of thermodynamics, isn't it supposed to be a purely physical science? And I would say, thermodynamics conceived this way actually is a blend of two kinds of considerations: considerations of physics and considerations of what kinds of things count as manipulable variables or ascertainable variables. And then you say, well, gee, does that mean that I can't apply thermodynamics to things in the distant past or far away from me, or things that I'm not in a position to manipulate? And I think the answer is, no, you misunderstood me, because when I talk about manipulable variables, it doesn't mean I'm in a position to manipulate them. It means it's the sort of variable that could be manipulated by an agent like me. So if a box of gas equilibrates in a distant galaxy and there's no agent around to manipulate it, there's still an increase of entropy as defined by a certain range of specification of what counts as manipulable parameters, because it's energy that could have been used to do useful work by agents, which could have agents suitably located, has been dissipated into a state where it can't. So, so that's the sort of answer like that. So it's definitely not meant to be restricted to things in the lab. Okay.
How much longer do you want to speak for?
What's that?
How much longer? Because just look at the screen. That might be
okay. I timed this well because, actually, let me see if I can get through, because I do want to actually get through soon. So maybe, maybe it'll enforce a restriction on the amount of time, right? Right. Okay. All right. Because actually, I'm not going to get. Sorry.
It's not the first one. It's not going to be the
it's all the best people.
All right. I just realized it's actually more than I want to do. I'm not going to get that.
But it's harder to be able to
All right. Okay. So these things that I've been calling epistemic chances. The characterization involves a couple of ingredients. One is, I'm assuming that wherever it came from, you have some judgment about which credence functions a reasonable agent can have above the microstate at time t0, and we can have a discussion about what those are. Reasonable, I mean, take it seriously. Actual reasonable person, and I don't mean, merely conforming to some very weak set of requirements like consistency or something like that. The example I used in the paper was inspired by James Garner character in a comic movie from the 70s called Support Your Local Gunfighter, which I remember watching on TV as a kid. And this character, I think like 2 or 3 times during the movie, gets this look in his eyes and becomes convinced that the result of the next spin of the roulette wheel is going to be 23, and bets all his money on it. And comic hilarity ensues. Okay, if you weren't in a philosophical context, you would all say, yes, of course, that guy's unreasonable. Some people feel obliged because they can't specify a constraint of rationality that guy's violating, because he can still satisfy probabilistic coherence and have those credences, to say, no, I do judge that reasonable, but you're pretending. So abandon philosophical pretense. You do regard that as unreasonable, and if you're stopping that guy and says, actually I do think I have the sort of detailed knowledge about the state of this room and the nervous system of the croupier, so that my credences are indeed concentrated on the set of microstates that lead to 23. You know, you don't know that much about the ring. That's all you have to say. And you know, that's what you would say if you were, you know, in a non-philosophical context, and your friend was about to bet all his life savings on 23. Okay. But I mean, there's more to be said about which, you know, how to cash that out with. So I guess, you know, take the judgments that you currently have. And suppose we have a dynamical map taking states at one time to another, and it induces a map to probability functions. We also implicitly make explicit that we have a tolerance for threshold for difference of probabilities below which we regard two probabilities as essentially the same. Then I'll say that, you know, a certain proposition A about the state of the system that T1 has an epistemic chance X if, sorry, there's an I missing there, if for any credence function in that set C, the time evolution of that credence function, I'm sorry, it should be any credence function little c, the time evolution of C yields a credence A equal to X within the, you know, within the tolerance threshold. So that's the definition. And notice it brings in both epistemic considerations and physical considerations. Now, having said that, this seems to me, at least if you have the Maxwellian view of thermodynamics and think of one task of statistical mechanics as recovering thermodynamics, this actually fits the bill well. And I will say it resolves the puzzles I started with, because they're introduced for epistemic considerations. And, but nonetheless, they're the sorts, if there is a value to this, you know, if there is such a number, this dynamical map is going to be doing a lot of the work in determining what that number is. So, you know, it's not just a matter of this, but it's a matter of this and this that determines that number. And so you can actually learn something about the physics when you actually learn something about the physics if you learn what that number is. And moreover, if I don't know this dynamical map T, or if I do know it and I can't do the detailed calculation, I might be in a position to have good reason to believe that there is such a number. You know, a number which is the probability which the time evolute of my credence function or any credence function I regard as reasonable, you know, yields for this proposition A, and have no clue about what, or be uncertain about what that number is. And I can do measurements. And because provided that my conditional I can be uncertain about what that number is, but I can have credences about what that number is, just as I can have credences about what chances are. And provided that my conditional credences satisfy the analog of the principle, I can test hypotheses about values of these epistemic chances by exactly the same procedure that I outlined earlier about testing hypotheses about values of chances. And that was the reason for that digression about testing, you know, getting evidence about chances. So I could, they call EC, let's say EC is epistemic chance of A. You know, I can have hypothesis of the form that the epistemic chance of A is equal to X. And then I can do a measurement of A. And provided my conditional credences, you know, if I have credences in propositions of this form, and I have a credence in A, and I have a credence in the conjunction of the two, then I can have conditional credences. You know, providing that my conditional credences satisfy the analog of the principal, then I will be able to do measurements and update my credences about what these epistemic chances are in just that way that I outlined earlier. So one feature that these things have is that, well, we just, go the list of the Desiderata. We wanted to make sense of the idea that we're introducing probabilities on epistemic considerations in the first place. We wanted, nevertheless, to be the sorts of thing to generate hypotheses. We wanted them to generate things that can be tested by experiment. And we also wanted something that wasn't going to land us into disastrous predictions. Well, I think that fits the bill. There's a temporal asymmetry built into this because of the temporal asymmetry built into this class C because of the temporal asymmetry of epistemic access that agents like us have. So there's that. You wouldn't expect them to be temporally symmetric in the first place. And also, they do come from the idea that they're there because we don't know the exact microstate stuff. Nonetheless, it makes sense to form hypotheses about their values and test those hypotheses empirically. Okay, I'm done.
Must be non-time recursive invariant. So at least I could imagine, so say a class of possible reasonable agents, more or less in the situation that David talked about. So the information they have maybe takes to only in one single instant, that the gas was at the left-hand side of the box. That particular information happens to be invariant on the velocity reversal. Suppose that's the information we have, and we're very reasonable otherwise.
Okay.
And now we apply our definition, we assume the dynamic matrix is sufficiently ergodic or mixing. We will get our epistemic chances for the future, and we will equally get our epistemic chances if we would look back.
Okay, very good. Yeah, very good.
And so they would both be equally objective, right?
Yeah. Very good. I don't disagree with anything you say.
Good.
Remember, I introduced this as a notion of probability that fits well with the Maxwellian view of thermodynamics. And the Maxwellian view of thermodynamics is, thermodynamic concepts are relative to, their means relative. They're relative to a certain set of variables that are the ones I think I can know about and manipulate. And fix such a set of variables, and you'll have a fixed distinction between heat and work and a fixed value of entropy for everything. But given another set of values, it'll be something different. I intend this to be relative to that set C in exactly the same way.
Yeah.
Given a dynamical map, then fix a set C, there's going to be a set of epistemic chances relative to C. Change C, you get a different set of epistemic chances. If there are agents for whom it is reasonable to have these temporally symmetric credences, I'm not sure, so grant you for the sake of argument that someone could be in that epistemic state, then if that set C is temporally symmetric, then anytime there's a epistemic chance towards the future, they're also one towards the past. I don't think we're like that, though. I mean, I am taking for granted that we have epistemic access to the past in a way which is different from the sort of epistemic access.
No, I can grant that, but I just wanted to tease out the idea that if, and as long as we're, if that is an allowed epistemic state, the inference to the future is just as rationally justified as the apparently disastrous influence to the past.
Yeah, I mean, now just starting to reverse exactly the stuff that David Albert was talking about yesterday. I mean,
if you just want to make clear what
if you don't know where the system came from, and I say, look, here's a gas that's spontaneously compressed to one side. And we know in the future it went that way, and most likely it came from a fluctuation.
I want to claim that this adds something more, because we just, with the fact about here, these agents have all this stuff about the past. I mean, when he said that you're getting an extra tool to add here when you're thinking of these epistemic agents and the things they might know, that goes beyond the...
well, if you have extra knowledge about how the system came about, and you're sure it's not a false memory, then absolutely, then the symmetry's broken.
Right, and really, what I'm really interested in is, agents like us.
In fact, it would very well be joined together in the sense that the extra information could just be there has been a Big Bang in the past, and I know that apart from every experimental information I get from my laboratory here, I must also assume that was the original state of the universe. And then you will have your time asymmetric credence.
Yeah, though I wouldn't single out cosmology. I would say your credences should be consistent with everything you know about the past. But and we had this discussion over dinner that a smaller constraint does the work if you just say have something like David's past hypothesis. I don't want to single out cosmology as special. I'm sorry, Nick has his hand up for a long time.
Yeah, I just wondered, since you are taking for granted special knowledge about the past, might there be a way to, might say something like this, I'm going to insist that these reasonable credence functions, or perhaps call them Schmidt's function or something to avoid insisting that actually what the agent believes, do have to be time symmetric.
What's that?
Could you just insist that the special functions that go in your set C do have to be time symmetric?
Do have to be time symmetric?
And then just say the rule for extracting implications of what I should believe from that are I should believe what the implications of that credence function is when I apply the standard microdynamics to it, except if it's trumped by the special knowledge I have about the past.
I don't know what that means, because a credence function is supposed to be my state of belief. And so if I know something about the past, that credence, or if I'm not certain, if on the basis of my memory, I have a strong belief that I said we break for lunch at 12:30, then that just means that I have credence close to 1.
Well, that's what I wanted to call the Schmidt's functions on this alternative view. It's going to be awkward to accommodate knowledge about the past in a particular credence function.
Why?
Precisely because it's going to be very complicated in phase space to get the credence function to match up with something that's going to give you behavior in the past.
A credence function that doesn't accommodate what I know, I don't know what that is, and I'm not interested in it. Not at all. Credence function is supposed to represent my state of belief.
Right, but it would be a probability function, and the predictions you got from that function would be correct if you applied a second step, which was you trump them if they clash with what you know about the past through this special source of knowledge which I haven't really explained. Anyway, that would give you the same result, won't it?
Yeah, that sounds like you start with something wrong and fix it. I'd rather not start with the thing that's wrong.